Dheeraj Tatar, a system professor in the Chemical Engineering Department of LJIT Ahmedabad. In this lecture, I am going to start new topic of the mass transfer operation 1. So let's start. Chapter name is interphase mass transfer and topic is chemical equilibrium. Before that, you should know the meaning of interphase mass transfer. In previous lecture, we have discussed in detail difference between intraphase and interphase mass transfer. Okay, and chemical equilibrium concept is involved in interphase mass transfer. Interphase mass transfer means there is a movement of the molecule, or I can say mass transfer from the higher concentration region to the lower concentration region between the phases, means between the more than one phase. That is interphase mass transfer. And in this phenomena, we are going to study now chemical equilibrium concept. So for this purpose, I am going to consider here gas absorption principle. Okay, so you can see here interphase mass transfer means mass transfer from one phase to another is called interphase mass transfer. Okay, I have discussed with you this concept in previous lecture as well. So what is the meaning of interphase mass transfer? Interphase mass transfer means there is the movement of the molecule between the phases, between more than one phase. Okay, and intraphase means there is the movement of molecule within a single phase. And the chemical equilibrium concept involved in interphase mass transfer, where interphase is separating two phases. That two phases are nothing but gaseous phase and liquid phase. Okay, these two phases are separated by the interphase. Okay, so here we are going to consider gas absorption principle. So you can see here, during interphase mass transfer, if no mass transfer occurs between the phases or the rate of transfer is the same on the both sides of the system, it is said to be in equilibrium. What is the meaning of this? Suppose there are two phases, gas phase and liquid phase, and these two phases are separated by the interphase. And suppose there is a movement of the particle from the gaseous side to the liquid side. For example, gas absorption. In gas absorption, one of the component of the gaseous mixture is removed by the liquid stream. Okay, so here movement of the molecule from the gaseous stream to the liquid stream is available, and both phases are separated by the interphase. So what is the meaning of equilibrium? If the rate of the transfer of that particular molecule is the same in the both side, means gaseous side to the liquid side and liquid side to the gaseous side is the same, or if there is no movement of the particle, that system is said to be in a chemical equilibrium. So for that purpose, I am going to consider here gas absorption in next slide. You can see here. Before that, you should know what is the meaning of mass transfer coefficient. So you can see here, I told you in previous lecture, for the liquid phase and the gaseous phase, there are different mass transfer coefficients are available. For liquid phase, that is given by KL, and for the gaseous phase, that is given by Kg. Okay, and overall mass transfer is represented by the capital Kg, capital KL. In coming slides, in coming lectures, I am going to discuss with you derivation for the overall mass transfer coefficient and relation among the overall mass transfer coefficient and individual or local mass transfer coefficient. But in this lecture, we are going to study mass transfer coefficient in detail. So in mass transfer, we are having mass transfer coefficient, and analogous behavior in heat transfer, we are having heat transfer coefficient. I told you that for heat transfer, we are having heat transfer coefficient, and for heat transfer, driving force is the temperature difference. So for mass transfer, we are having Kc, that is a mass transfer coefficient, and driving force is the concentration difference. So in engineering, chemical engineering, the mass transfer coefficient is a diffusion rate constant that relates the mass transfer rate, mass transfer area, and concentration change as the driving force. So how to represent this relation? You can see on the screen, the amount of mass transfer is directly proportional to the concentration difference and interfacial area. Okay, concentration difference means suppose difference between the concentration of component A at the surface and bulk phenomena. I am taking CAS here. CAS is nothing but concentration of component A at the surface, and CA is nothing but concentration of component A in the medium, or I can say bulk, at any point in the bulk or at any point in the medium of the particular phase. Okay, so you can see here how to represent this equation now. Amount of mass transfer is directly proportional to the interfacial area and concentration difference, and proportionality constant is K. This K in this equation is nothing but mass transfer coefficient. In the similar manner, we have seen for the heat transfer, there is the Q by A is directly proportional to the temperature difference, and proportionality constant is small h. Okay, so this is the equation. This equation can be asked for 3 marks, means what is the relation between mass transfer and interfacial area and concentration difference. So you have to write here like this: amount of mass transfer is directly proportional to the interfacial area and concentration difference, and that proportionality constant K is nothing but mass transfer coefficient. Okay, so this question can be asked for 3 marks in your final examination. After that, now we are going to study here chemical equilibrium concept. So for chemical equilibrium, I told you we are going to consider here gas absorption phenomena. So in gas absorption, there are 2 streams. First one is gaseous stream and liquid stream. Okay, so listen carefully. We are going to remove one of the component from the gaseous mixture by using water. So here we are going to consider gaseous mixture, and from that mixture we are going to remove NH3, ammonia molecule, by using water. We know that ammonia is soluble in the water. That's why we are considering here amount of the ammonia. That's why we are going to consider here extraction of the ammonia from the gaseous mixture by using water stream. Okay, so you can see on the screen. As an example, consider the gas absorption operation which occurs when the ammonia is dissolved from ammonia air mixture by liquid water. Means here we are going to consider one container, and in that container we are going to add this gaseous mixture and water. So you can see here, suppose a fixed amount of the liquid water is placed in a closed container together with a gaseous mixture of ammonia and air, the whole arranged so that the system can be maintained at constant temperature and pressure. So here we are having one container. In that container we are having one mixture which contain of the ammonia. Okay, that's why we are going to remove that ammonia component from that gaseous mixture, and in the same manner we are also having fixed amount of the water. So in the container we are having mixture of air and ammonia and water. So here water is extracting part of the ammonia from the gaseous mixture. So how this phenomena takes place, you can see on the screen. Since ammonia is very soluble in water, some ammonia molecules will instantly transfer from the gas into the liquid. Solubility of the ammonia is very large in the water, that's why it instantly move from the gaseous mixture to the liquid, that is nothing but water. So as the crossing the interfacial surface separating the 2 phases. After that, there is the reverse phenomena that is responsible for the chemical equilibrium. See there, a portion of the ammonia molecules escape back into the gas at a rate proportional to their concentration in the liquid. What is happening in gas absorption? We are removing part of the ammonia from the gaseous mixture into the water stream. Okay, but at the same time there is a reverse phenomena also takes place. Means whatever the ammonia is dissolved in the water stream, that is escaping back into the gaseous mixture. Okay, so this rate of backward reaction is increases. So a portion of the ammonia molecules escape back into the gas at a rate proportional to their concentration in the liquid. So as more ammonia enters the liquid with the consequent increase in the concentration within the liquid, the rate at which returns to the gas increases until eventually the rate at which it enters the liquid exactly equal at which it leaves. What is the meaning of this? Means whatever the ammonia is escaping into the water, okay, means this is the forward reaction, and backward reaction means ammonia escaping again back into the initial mixture. Means movement of the ammonia from the gaseous mixture to the liquid mixture, and again from liquid mixture to the gaseous mixture. Means there is a forward reaction as well as backward reaction. Whenever the rate of the forward reaction and backward reaction is the same, or there is no transfer of the molecule in these 2 phases, at that time I can say there is the equilibrium exists. I am repeating, in this phenomena we are removing ammonia particle, ammonia component from the gaseous mixture by using liquid stream. Okay, this is the forward reaction. But at the same moment, some ammonia part is escaping back into the initial mixture, that is nothing but backward reaction. When the forward rate and the backward rate is equal, at that time there is the chemical equilibrium. Or if there is no movement of the particle in the forward reaction and backward reaction, at that time I can say system is available in the equilibrium. So you can see at the same time through the mechanism of diffusion. Diffusion means there is the movement of the particle from the higher concentration region to the lower concentration. The concentrations throughout each phase becomes uniform. Means I told you in diffusion there is a concentration gradient is a must. What is the meaning of concentration gradient? Difference in the concentration of the particular component, okay, for which there is a diffusion takes place. But at equilibrium, the component composition in both the phases, gaseous phase and liquid phase, is the same. At that time, I can say there is a chemical equilibrium exists. So this is the meaning of this last point. At the same time, through the mechanism of diffusion, the concentrations throughout each phase becomes uniform. Means there is no difference in the concentration, there is no concentration gradient is available. At that time, I can say a dynamic equilibrium now exists. And while ammonia molecules continue to transfer back and forth from one phase to the another, the net transfer falls to 0. Means there is a rate of forward reaction is equal to the rate of backward reaction. Means there is no movement of the particle from the gaseous side to the liquid side and liquid side to the gaseous side. At that time, I can say dynamic equilibrium is exist. So this is nothing but your chemical equilibrium concept in interphase mass transfer. And the concentration within each phase no longer changes. This is all about the interphase mass transfer chemical equilibrium concept. So what we have seen in this lecture, I have discussed with you how to represent the chemical equilibrium concept, facial area. Okay, that relation can be asked for 3 marks. That is nothing but amount of mass transfer is directly proportional to the interphase area and the concentration difference, and the proportionality constant is K. After that, we have seen in this lecture very important concept, that is chemical equilibrium concept in a diffusion, or I can say interphase mass transfer. Okay, means whenever, and we have considered here gas absorption principle. In gas absorption, we are removing one of the component from the gaseous mixture by using liquid stream. So here we have taken the example of the liquid air mixture, where we are removing ammonia by using liquid stream. That liquid stream is nothing but water. We know that ammonia is soluble in water. Okay, and chemical equilibrium means a dynamic equilibrium exists when forward reaction and backward reaction having same rate, or I can say there is a no concentration change is available, or I can say there is a no concentration gradient is available. Concentration of ammonia is the same in the liquid side and the gaseous side. At that time, I can say there is a no concentration difference is available in the both sides. This is all about this lecture. We will see next topic in the next lecture. Thank you very much.